Well, we've already talked about the idea of hypothesis testing came up when we were talking about the banana game, right? And we were saying if someone did end up getting 4 bananas in that game, if someone did end up getting 4 bananas when they were playing that game and they played it 5 times, that would make us think, oh, this is someone actually whose probability of knocking a monkey off a branch is not 0.3. In fact, we actually think that for that person, their probability is different. And that's really what a test is. We're trying to say, well, let's look at some information and try and find out whether the thing that we had assumed to be true, let's actually find out whether our assumption was correct or not. And that's what a test really is all about. I think the reason we find hypothesis testing confusing is because it feels like there's lots of new kind of like language that surrounds it, but we don't really need to worry about that language too much. So we're going to just talk through this idea instead with flipping a coin rather than monkeys on a tree branch in a video game, okay? So it says, I throw a coin 10 times. For what numbers of heads might you conclude that the coin is biased towards heads? Now, if you probably asked someone this when you're lower down in the school, they might have said, oh, well, if I flipped the coin 6 times and I got, if I did the coin 10 times and I got 6 heads and 4 tails, someone maybe in year 9 or year 8 would say, that must mean that it's biased towards heads. But we know from the binomial distribution that actually there's still quite a big chance of getting 6. You're not always going to get 5 if you flip it 10 times. But there's going to be a certain point where if it gets quite extreme, you might say to yourself, actually, this doesn't feel like just a random occurrence of getting 10 heads in a row. This might make me think this coin is got something that's weighting it to one of the particular sides, okay? So what it says here, it says that a hypothesis is a statement made about the value of a population parameter that we wish to test by collecting evidence in the form of a sample. That sounds really confusing. What it's really saying is a hypothesis is saying what we think is true about a particular thing and a particular probability that goes with it. We're going to collect some evidence and we're going to find out whether we think that is true or not. For some reason, this bit hasn't printed properly, but this bit should say, so you can add this in, the null hypothesis, which we do with h and a 0, is the default position, i.e. that nothing has changed unless proven otherwise. So in this particular case that we've got here, the default position for this coin is that we think the coin is fair, that the probability is 0.5. And null hypothesis, null is another word that means nothing. So we're just saying this is the hypothesis that we just think is normal, okay? The alternative hypothesis, H1, is that there has been some change in the population parameter. There has been some change in this probability of this particular coin. So the alternative position here is that the coin is biased towards heads, i.e. P is more than 0.5. In this context, I should have said here, the thing we're asking about, is the coin biased? This is making a statement about the probability P of getting heads in this coin flip. So for this particular thing that we're talking about here, this blue range that I've got is probably going to be something where we wouldn't think that it was biased towards heads, okay? If you got no heads, 1, 2, 3, 4, or 5, we definitely wouldn't do that if we did a result of this and think, oh, it's biased towards heads. Especially if you got no heads or 1 heads or 2 heads, you would never think, oh, this coin is biased towards heads. You'd be like, what? That doesn't make sense. But if you get to this region down here where these bars are quite small, that is where you should be thinking, this is a really rare thing to have just happened by itself. It might happen, but we know that if you were to get 10 or 9 heads when you flip a coin 10 times, that's pretty rare for it to happen. So I've said here, for this range of outcomes, we would conclude that this number of heads, 9 or 10, was too unlikely to happen by chance, and hence we would reject the null hypothesis, which is saying that it's fair, and instead we would accept that the coin was biased towards heads, and it depends on what probability that is. So if this region down here adds up to a percentage that is very, very small, that makes us think that is so rare that could happen that instead of it being chance, we think that maybe the probability is not 50-50 for this coin and that something has changed. However, if this probability adds up to it and it's 4%, it doesn't mean that just because that's less than the significance test, which we'll see later, which is less than 5%, it doesn't mean the coin definitely is biased. It just means in that experiment, it's quite unlikely that that happened by chance. It's quite unlikely that there was a 4% chance of that happening. But it doesn't mean it couldn't have happened. Because obviously if you did it 100 times, 4 times, you would expect that kind of thing to come up. So on the next bit, there's a bit more language that comes around this as well. So the level of significance, alpha, is the maximum probability where we would reject the null hypothesis. This is usually 5% or 1%. What that actually is saying is, if the chance of flipping a coin and getting 9 or 10 heads, if that is 5% or less, that's quite rare to happen by itself if it was a fair coin. If it goes less than 5% or less than 1%, which we randomly decide what is the level of significance there, what we're saying to ourselves is that is so rare to have happened by chance, by a binomial distribution with a 50-50 chance of head and tails, that what we actually are thinking, maybe the probability isn't 50-50. Instead, the probability is more weighted towards heads because that's the thing that has been happening. So here in this context, I've said if we saw a number of heads within ranges of outcomes that were sufficiently unlikely, then we would rule out that that coin is fair and conclude that it was biased. But how unlikely is sufficiently unlikely? Well, if alpha is 5%, if the significance level is 5%, then we would find a region of outcomes where there's at most a 5% chance of one of these extreme values happening by chance if the coin was fair. So here, if alpha is 0.05, we've set this region so that there's at most a 5% probability of seeing these number of heads by chance. It will make more sense when we look at it with some examples, but the idea is comparing how likely is it that something happened by chance versus how likely what the significance level is. And if it's less than that particular thing, we say, hang on, something seems up here. There must be something different about the probabilities. So this, I think, in a nutshell, is probably quite useful to read through. So number one, we have some hypothesis we wish to see if it's true, e.g. that a coin is biased towards heads or that someone has a stronger probability of knocking a monkey off a tree in the video game. That's the thing we're interested in trying to test if it's true or not. We collect some sample data by throwing the coin or playing the game, giving us our test statistic, and if that number of heads or more is sufficiently unlikely to have emerged just by chance, then we conclude that our alternative hypothesis is correct and that the coin is biased. So let's put this in context that might make might give it a bit more understanding of things that could happen. So the idea of a null hypothesis and an alternative hypothesis. This one doesn't really need any writing down because I decided to print all of this so you could just read through with me. Let's see what the question is saying. An election candidate believes she has the support of 40% of the residents in a particular town. A researcher wants to test at the 5% significance level whether the candidate is overestimating her support. The researcher asks 20 people whether they support the candidate or not, and 3 people say that they do. Write down a suitable test statistic, blah, 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 that we've got here. Well, let's just not even look at the questions for a second. She's saying, this particular person who's trying to become an MP or get elected to the council, whatever it is, she thinks that 40% of the residents support her. If you ask 20 people, how many people would you expect to support? 8 people, okay? So that's 40% of 20. So this researcher wants to find out if this is true or not. And actually this researcher thinks that she's lying and saying that she's got 40% of people supporting her. They've gone and done a survey with 20 people. And instead of there being 8 people, only 3 people said that they support this candidate. And what we're really trying to find out here is that just something that could have occurred by chance? Or is that something that could have occurred by chance but was very unlikely to have occurred by chance? If it was very unlikely to have occurred by chance, that makes me think that the election candidate is wrong and that she doesn't have 40%. She's actually got less than 40%. There is one last thing to say on that before we actually look at the question. If the probability that there are 3 people or less saying that they support her, even if it's small, even if it is 1% or 2% or something that's less than 5%, it doesn't definitely mean that this has changed. It just could be, 1 in 100 times, the 1% chance is going to happen. Okay, but in terms of a hypothesis test, it gives us enough evidence to suggest that the politician is wrong. Okay, so it never tells you for sure, because this is the real world. We don't know these things until we have the actual election. Okay, so you can't actually know these things. These are all about trying to make predictions. So the suitable test statistic, we talked about this in the last lesson. The test statistic is the number of people who say that they support the candidate. It's like, what is the thing that's actually we're looking for here? So in a hypothesis test, the evidence from the sample is the test statistic. For the binomial, the test statistic, is very difficult to say, is always the count of the successes. So if they ever ask you that, it's a 1-mark question that is free, gives you 1 mark. Now, the 2 suitable hypotheses, I'm sure you're good at this already. You write null hypothesis, H0, and you put ... That's the thing that we're saying, okay, well, we're just going to presume that the election candidate is right, and we're going to say that her support level is 0.4. But the researcher who is interested to try and say that, thinks that she's lying, or that it's not true, they think that the support is less than 0.4. Why is it less than 0.4 and not greater than 0.4? Why is it less than 0.4 in the context of this question? Yeah, Muzakir.
It's actually overestimating, so the researcher thinks she's gotten bigger than it actually is.
Yes, so it says that she thinks she's overestimated. There is another piece of information in this question that tells me that the alternative hypothesis is that the probability is less than 0.4. Hamza?
It says only 3 people support it. However, we did 40% of 20 which gave us 8 people.
Fantastic. We thought the expected amount would be 8 people, but there's only been 3. And so 3 is obviously less than that, which makes us think, okay, well, it's going to be less than 0.4. So the question gives us a clue in 2 different ways of what that is. So I've said this here. The alternative hypothesis is the candidate is overestimating her support. We're interested when less than 40% of them, more than 40% would not undermine the candidate's claim. So the last thing says, explain the condition under which the null hypothesis would be rejected. So the null hypothesis, which is this one up here, would be rejected if the probability of 3 or fewer people supporting the candidate is less than 5%, given that the probability is 0.4. So I don't even really need to worry about that last section of it here. We're saying if the probability of less than 3 people out of 20, if that ends up as being quite a rare thing to have happened by chance, that makes us think that the researcher is correct and this election candidate's chances of getting voted are lower than 40%, which is basically what I've just said in this section down here. But we always will look at the probability of it being 3 or fewer, always more extreme in that direction of the probability that we're talking about. And the reason we pretend that it's 0.4 is because that's the thing we're testing. That's the thing that we presume to be true. So let's have a look at another one of these together. And then that's us just going to finish up on this bit of hypothesis testing, and then we'll move back to mechanics, okay? So it says in the UK, 5% of students turn up late to school each day. Mr. Bison wishes to determine to a 10% significance level if his school, Morpeth School, has a problem with attendance. He stands at the front gate one day and finds that 6 of the 40 students who pass him are late. Write down a suitable test statistic. So the test statistic, and I can't wait to not have to say this word, is the thing that we're measuring. So what's the thing that I would measure when I'm stood at the school? The number of people arriving late. I should really have just said stood outside WW205 after break time, seeing who comes in the room. And the 2 suitable hypotheses, right, so obviously the null hypothesis is that we think, we're just going to presume that Morpeth School is exactly the same as the rest of the country. So what's the probability of someone being late? 0.05, 5%. Now, this is the thing where I haven't said, oh, I think that we're overestimating it or underestimating it. So there was some extra information, and I found that 6 out of 40 students. Does that seem like a lot of people or not a lot of people? 15%. That's a lot of people that have turned up late, okay? So I actually think, my alternative hypothesis, I think that Morpeth has more than 5% of people are coming along. And I'm really trying to say, well, actually, if I did this measurement and I worked out the binomial probability that there were 6 or more people late out of 40, if that was really, really rare at the 5% probability, then that makes me go, actually, Morpeth has got a problem with attendance. Okay, because we're so far above. This couldn't have happened just by chance. I actually think this is so far above. So the condition under which the null hypothesis would be rejected would be if the probability of the number of students being late to school was more than or equal to 6, if that is, when would it be rejected, the null hypothesis?
1 degree x.
When it's less than 0.05.
Good. It's if this was less than 0.1 actually, because we're looking at the 10% significance level. So if the chances of 6 or more people coming to school late was less than 10%, that makes me think that's pretty significant, because a 10% chance of something happening is sort of rare, okay? I mean, we can actually just finish this question off. Let's actually just find out what is the probability that someone is greater than 6, given that x is binomially distributed, there's 40 people coming to school, and we think the probability for the whole country is 0.05. Yeah, we can do it with the tables. So we've got 40 people coming to school and 0.05. So we've said 6 or greater. Well, this is 5 or less. So we're going to do 1 minus 5 or less, 0.9861. So the probability of x being greater than or equal to 6 is 1 minus the probability of x being less than or equal to 5, which is 1 minus 0.9816, did I say?
Yes. 9861.
9861.
That's a B.
Which is 0.0139. So let's just, because it actually makes sense to do a full kind of hypothesis here. So this probability, this is the chance that more than 6 people were late if Morpeth is exactly the same as the rest of the country. As a percentage, this is 1.39%. So there is a 1.39% that Morpeth is just the same as the rest of the country, but it just happened to be a rare occurrence where 6 people were late that day. But that is a lot less than the 10% significance level. If I was going to place my bets, I would say this is so rare, 1.39% for something happening, that I think that actually Morpeth does have a problem with its attendance, and that Morpeth's, the chance of people being late at Morpeth is higher than 5% because it's such a rare thing. And that's because the statement is 0.0139 is less than 0.1. So there is enough evidence. There is enough evidence to reject the null hypothesis. So I'm just going to state this again. I know it sounds like I'm just repeating myself, but in this particular scenario, 6 people was quite an extreme thing to happen, that many people being late. So if I check what is the probability that 6 or more people, it's always more extreme in the direction of the thing that we're thinking about, the probability that we had 6 people out of 40 late, if we were the same as the rest of the country, is only 1.39%. That's a pretty rare occurrence to have happened. Remember, it could happen in a rare scenario. That's a pretty rare thing to happen by chance. That is less than 10%, which makes me think this is a significant discovery that we've seen here, that 6 out of 40 people. It's so significant that it makes me think that the probability for Morpeth is not 0.05. It's actually higher than 0.05 because we've been looking at it in that direction. I didn't mean to do the full hypothesis test that we've done here. The questions in exercise 7A are really just stopping at this particular point here, but I thought it kind of made sense to have a look at some of that as well. So when we do this after the half term, we will do some full hypothesis tests, but this is kind of the idea. What's the likelihood that it happens just by chance through binomial versus do we think something is different there? Do we think that it's, do we think something significantly has changed? Are there any questions on this before we go back over to mechanics? Yeah, Hamza.
What do you mean there's not enough evidence to reject?
There is enough evidence to reject the null hypothesis.
What's this evidence? So when do you
So
know
the evidence is that 6 people out of 40 were late, okay? And we've said if 6 people or more were late, the chance of that happening is only 1.39%, which is enough evidence, because it's less than 10% here. That's enough for me to think this can't be true. So I'm rejecting this. I'm saying I don't think the probability is 0.05. I actually think the chances of people being late to school at Morpeth at this particular time is more than 0.05. And we normally talk about rejecting or accepting the null hypothesis because we don't know for sure that the probability is greater than 0.05. We don't 100% know that because there's a 1.39% chance that this could have happened. And if you imagine 100 schools were all doing this experiment and 100 schools had 6 out of 40 people that were late, for one of those schools out of the 100, they don't have a problem with lateness. They just happen to be the one school that had that probability. But 99% of schools who did this experiment and got 6 out of 40, they have got a higher likelihood of people being late than 0.05.
An anomaly.
It's an anomaly, yeah. So like it could still happen as an anomaly, but it's a 1.39% chance of that happening as an anomaly. And because 1.39 is less than 10% in this case, that means that it's not. We're pretending it's not an anomaly, and we're going to say actually we think this is significant. We think that we do have a problem with lateness at the school. Okay. So it's all about saying an anomaly versus is it significant, and usually we do less than 10% because 10% is not that significant.
We would accept the null hypothesis.
We would accept the null hypothesis. If it was greater than, we don't have...
We wouldn't have a problem.
No, we think that it's not that rare to have happened. Let's say it came out and it was, I don't know, if I did something different, if we said what's the probability that x was greater than or equal to 4, that's 1 minus the probability of x being less than or equal to 3. So let's just have a quick look at what that would be. 8619. So you get 0.1381. So there's a 13% chance of 4, 5, 6 or more people being late. 13% chance, yeah, like it's still rare to happen, but it doesn't make us think it's so rare that we've got a problem with lateness. It just makes us think, oh, maybe this was just a particularly bad morning amongst a bigger picture of things that are a bit more normal to happen. Because like we said at this beginning thing, if you flipped a coin and you got 9 in a row or 8 in a row, yeah, you'd be like, that's kind of extreme to happen, but it doesn't necessarily mean the coin is biased. Okay, it just suggests that it is biased depending on the probability of that happening. So we're going to do many, many more examples of these across the next few lessons, or next lesson, and it will become clearer. Every time I talk about it, I'll talk about it in that same language, and it should make some more sense, okay?